So that's Wednesday. We already have the first routing algorithm. The first routing algorithm talking about the link state. Link state routing algorithm. And after that one, today we will already have the distance vector routing algorithm. It's a distributed routing algorithm. Well, so let us start this one. Distance vector routing algorithm. Distance vector routing algorithm we will pass on the key equation. It is called the Bellman-Ford equation. And in fact, you have the Bellman-Ford equation that's this one. I don't know, we know the Bellman-Ford equation a few weeks ago. We have the intermediate node V, and we want to test, is it possible to have the beta path, the least cost path? We can pass on V, and if any V, we can have the update. Then we have the update from source node to destination node. Source node to destination node V. So this is the Bellman-Ford equation. Well, therefore it says we know X to V, and then we want to know V to Y. V to Y known by the node V already. Well, we want to have the least cost path update. Well, actually we can pass on this one to have the possible update. So let us check how to have the update. So we know the distance vector. Assume we want to know these. We have intermediate node V, intermediate node W, intermediate node X from the source node U. Therefore, we have the source node U and destination node Z. And currently, V, X, and W all are the previous description node V. So we choose the intermediate node V, and currently we have a V already. And also we can have a X and have a W. And we have the given value. Maybe you have a question why we know that one. Assume even it's wrong. But we have the given distance vector. Therefore, we have the Bellman-Ford calculation. We want to find the least cost path. Well, we have 2 plus 5, 1 plus 3, and 3 plus 3. Sorry, 5 plus 3, and so that we have the minimum one, it should be 4. And if 4, this is the minimum one, and in the past we don't have the least cost for this path, then we need to have the update. Well, you see, this node will achieve the minimum cost path if we have the new enough one. If new enough one, then it is a distributed one, so we will have the update for that. Well, so the key idea, in fact, we want to pass on the Bellman-Ford equation to have the update. You see, Bellman-Ford equation. Well, for some reason, maybe we can have the update, then we need to broadcast to the neighbors. Well, so each node we need to wait any change. All right, any change. So any change in the local link cost, if changed, then we'll have some update and or messages from the neighbors. Likewise, we will have the update for sure. And then we will have the recomputation based on the Bellman-Ford equation. After computation, then we need to notify the neighbors. Well, so the key idea, if necessary, we will have the recomputation. And once we have the recomputation, of course, you can check. We have the update already, or maybe no. If no, then it won't be necessary to notify your neighbors. And here we assume yes, we need to notify. And this is a loop. Right? So we also want to keep the new enough updates. If yes, we need to update, then we need to notify our neighbors. It's an iterative asynchronous manner. But later we will assume we have the synchronous manner to have the illustration. So in fact, it should be asynchronous, 非同步. And we have the iterative, I think you know this one. But later we will assume we have the synchronous manner to have the update. Well, of course, we expect the operation can be the distributed and self-stopping. Why self-stopping? In fact, if we have the update message, then we will send. If no, then we stop it. So it's the self-stopping algorithm. Therefore, no update, then no notification sent. Well, right now, this same vector, and we just pass on the Bellman-Ford equation to have the example for initialization, for the recomputation, for the notification. And we assume we start from time 0. And time 0, currently we have a node A, and assume we just know this sum vector to the neighbor. So you see we have a D, it's 1, and we have a B, it's 8 from node A. Right? So we have something, of course, we have the missing links. All right. Well, so currently, the current time, all nodes have the possible estimates. And initially, if we just have the information to the neighbor, it doesn't matter. All right. And of course, all nodes. Right? Once all nodes have the update information, then we will have a notification. All right, so you see, we have the notification. Well, so even it's the initial time instant, we have the notification because we have the new information to be sent to the neighbors. Well, iteration. Previously, we didn't know this is the iterative manner. And we have the asynchronous manner. Well, think about this. Okay, maybe we have the different time instant. Time instant, maybe A, I send the update to my neighbor. But you don't send the update simultaneously. So we should have the asynchronous manner. But right now, we assume no. We have the synchronous. We assume we have the synchronous manner. All right, so we have the information update synchronously. So we will have the new message from neighbors, and we will compute again. And likewise for 2, compute. Alright, so and so on, we will have update, recomputation, update, recomputation. Oh, sorry, update, recomputation, and notification using the loop. And so that look at this. Currently at B, right? We have the current information. And we have A, and we have C, and we have E. Why we choose A, C, E? Because we just choose the neighbors of node B. Well, based on the information, it's update. So the information update by neighbors A, E, and C. And then we will have the computation. Here I call it the recomputation. And computation, how to do? Look at this. B to A. Alright, B to A, then we will have the information B to A. It should be BA and then A to A. And again, B to A, we have a neighbor C, so we will have B to C first and then C to A. And B to E, E to A again. Well, for this example, of course, I will that you have the information, the detailed information. So at least for the update, we can have the information A to A, well, it's 0. And C to A, here we have infinity. And E to A is infinity. And about the link cost, here we have 1 and 1, but this is 8. Sorry. It's 8. So finally, we will have an update. Currently, it's 8. So it's 8, even we have the recompetition. Still, it's 8. So no update for this. Same. Right? However, we have the recomputation for the others. And B to C, it's 1. And B to D. Here, B to D, previously we have infinity. Right now we have 2. And we can continue. And so that we have the possible update for B. Right? So you can have the new result for distance vector in node B. We have 8, 1, 2, 1, 2, infinity, 2, and infinity. And this current table is different from the old table. Well, if you pass on new and old, here we have the new table. Of course, you need to update because we have the new information. Right? So B will notify neighbors. And of course, we pass on the computation of node B. And B get the new table. Of course, B will have the update. Update then need to notify. You see, notify the other nodes. And for example, to C, C will have a recomputation later. Alright, so you see. Alright, so we choose node C. Currently, we choose node C because node C only connect to B. And B, this node allow table, distance vector table in C to have the new result. You see, same. Similarly, we have the computation. And so that we have the new table in C. And new table in C actually will replace the original old table. You see, this one. Replace, and then we'll notify the others. Alright, so currently we have computation at node B and computation at node C. And so that we have the update, this one and this one. In fact, we have a synchronous or asynchronous. Possibly we will have the synchronous manner for the update, or otherwise we don't have the synchronous information. So if necessary, we will have the synchronous transmission. Well, this is the application of distance vector update using the Bellman-Ford equation. After now, allow you to think about based on the current table. In fact, in the following, we have a few similar steps, and later maybe I may skip. However, stay here for you to have the discussion with your neighbors, even maybe no. But think about this. Okay, let me check. It should be H. Yeah, something wrong. That's correct. Yeah, about the current page. Some of you find, okay, we should have the notification change. C here should be changed to H. All right, because currently we have the node H. All right, we always maintain the distance vector from the current node. So in fact, H, of course, you should have H to the other nodes, H to A, H to B to the others. So this one actually is something wrong. We should have the modification for this one. All right, so this one actually we already have the distance vector update using the Bellman-Ford equation. And same, we can have the computation at the current node E. All right, so I go through quickly. Well, therefore, this update says we have state information diffusion. All right, it's diffusion. Even right now, we don't talk about AI. Still, we have the information, state information diffusion. Using update, if we have any information update, then we will diffuse the state information to our neighbors. And diffusion. And here, why we talk about diffusion? Diffusion says we will travel. Information will travel. So look at this. We have something like we have a web. Web, then we will diffuse. Right? So do you feel the diffusion? We have the web, and then the information will propagate from the current node. For example, the current node is C. C to the first hop, to the second hop, to the third hop, to the other hops. So we will have the effect of a diffusion. Why it's a diffusion? Because we can have a relay. Right? Relay says we have an update to my neighbor. My neighbor will update to its neighbor. So we have a relay. And once we have the relay, then we can have the possible diffusion, state information diffusion. All right, so this way, this says, can we pass on diffusion to have the distance vector update? Yes, don't worry. We can have the update based on the state information diffusion. All right, so diffusion, so we pass on 0, 1, 2, 3, 4. That says yes, we can allow the state information to propagate or here diffuse to the neighbors. And from hop 1, hop 2, hop 3, and hop 4 neighbors. All right, and of course right now we have hop 4 only. So you can consider if we have a large enough network, then we can have the others. Well, up to now, we have the fundamental idea of distance vector algorithm. What are they? We have the information update, computation, notification. So we pass on the loop, information update or not, if yes, computation. And computation check, should we have the different information? If yes, update, using the loop to notify the neighbors, and so that we can maintain the state information for the entire network using the distributed manner rather than the centralized manner. Alright, so this is the key idea of distance vector. And so that if you want to have the next hop, of course you will pass on the DV in a specific node to have the decision which output link you need to go. Well, up to now, this is the main idea of the distance vector based on the Bellman-Ford equation. Alright. And next one, yes, Bellman-Ford equation. Think about Bellman-Ford equation. Choose the least cost. Least cost path. So least cost path says the good path. Right? The good path. Because of the main idea, Bellman-Ford equation wants to choose the best, to choose the good path. Rather than, right now, maybe not good news, it's bad news. Alright, so later we will check if we have a different situation. Right now, the link changed to a really large cost. So, can the network reflect the change for the large cost link? The answer is no. Change slowly for the large link state update. Well, because of a Bellman-Ford equation, so we have good news, travel fast. Alright, good news, travel fast. And how about this? We want to know this one. Good news, travel fast because of the Bellman-Ford equation to choose the least path cost. However, I want to emphasize this one. Well, the previous one, link cost is 4. And how about change it to 60? And here we have bad news for the link cost. However, bad news, travel slow. Because the target of a Bellman-Ford equation, we want to choose the best one rather than the worst one. Therefore, bad news, travel slow. And here we have some description. Yes, even for the small network. Based on the previous iteration, you will find, we use many steps and so that we allow the whole network to have the update to know, yes, the current link X and Y became 60. Alright, became 60 in the past, but we know that one really late. Well, so this is the disadvantage of the distance vector algorithm. Knowing the best one fast, but knowing the bad one slow. Alright. Okay, so the problem for distance vector, if we have the bad cost, then we will know that one slow. Well, slow, is it a problem? Yes, it's a problem. If I want to choose this cost path, however, right now the link changed from 4 to 60. Of course, we won't send the message to go through X and Y for the previous network. And therefore, it will be reflected slowly. reflect it slowly, then we will always send a message to that path because we think, okay, everything's okay. So we will have the wrong direction of the message to the wrong path. All right, so we didn't have the main idea of distance vector, and also didn't have the problem. Bad news travel slow for the DV because of the Bellman-Fold feature to find the least cost path. And right now, we put them together to have the comparison between link state and distance vector. Well, talking about the disadvantage of link state, previously it should be acceleration. And current one, distance vector, the problem should be if we have the bad news in the network cost, then we will know that one slowly. So after that one, right now, we will already have the comparison using the complexity. Message complexity says how many messages sent in order big O. And this page just for your reference. Once you have some knowledge about the big O notation, or maybe some of the idea from the algorithm or from the data structure, then you will have the possible big O notation associated with this. Here we have link state and distance vector. And the link state, yes, we can have the big O notation. However, for DV, we don't have the specific big O notation because it pretty depends. 也就是它会随时间不太一样。It pretty depends, so we don't have the big O for DV. So this is the first one, message complexity. How many messages sent through the algorithm link state, through the algorithm distance vector. And next one, speed of convergence. That says time complexity. All right, and for link state, same, we have n nodes, so the order is big O. All right, and we have the problem, oscillations. And for DV, yes, it pretty depends, so we don't really have for that one. But slow problem, okay, I don't mention the specific term. This term, count to infinity says bad news. Travel slow. So that problem we have a term, count to infinity. Why we use the term count to infinity? Count to infinity takes you a long time. So that says bad news travel slow. So bad news travel slow, we have a specific term associated with the distance vector. Count to infinity. Problem of or issue of count to infinity with the distance vector. So acceleration associated with the link state. Count to infinity associated with the distance vector. And next one about robustness. If we have a router malfunctions, or maybe compromise. So how about the link state? Wrong information. So we will have the incorrect link cost because of the link state. And wrong link cost and only for the node. All right. Because of a link state only for the node, so it won't propagate the information because each node computes its information. Even we know the entire topology of the network. But distance vector will advertise the passcode. So we will have the propagation and error will propagate to the network. So you see, it says about the robustness, distance vector will propagate the error caused to the entire network. And so that if anything wrong with the information, DV will get worse. And even worse than the link state. So about the robustness, link state will be better. Why link state will be better? Under the assumption link state know the whole topology of network. So under the precondition, knowing all the information. However, knowing for all the information is the burden of the algorithm, link state. Well, so even link state will provide the robustness, however, it needs to have the extra burden. All right, so last week we already have the link state algorithm, and today we already have the distance vector algorithm, and we put them together to have the comparison. And the two algorithms actually are the fundamental routing algorithm. And currently, let us have the attendance check-in first. Well, for me. All right, so let me move on. And next one, I will ask you to think about. Currently, I already have the link state routing algorithm. Distance vector routing algorithm, we think about the two algorithms. Do you, do you understand well, or you still have some places to ask me to re-explain? And of course, don't forget to have a UID name and good ID. And currently we have a good 1 and good 3. Yeah, good 3. And good 6 in the classroom. Also, the other members online, I think you choose your one. And yes, we will have the activity. Think about this and check it, same, 2 minutes. So your name, your name and ID. And good ID, yes. So wait for you for 10 more seconds. All right, time's up. So again, let me move on. And we have the estimate, it should be 2 minutes. So I close it and go to the next one. If you fail to have this, of course, you can use line good to let me know. And so that we still can count your points for you. So up to now, we finished the discussion for the distance vector algorithm. And next one, we will have the more detailed description. So maybe you can think we have the advanced or the realistic routing algorithm. And we will have two categories. The first category is the intra. Intra says within the subnet. Inter, then we have a routing among ISP. Inter says we have a subnet 1, we have a subnet 2. Subnet 1 and 2 need to have the routing. And so that it's BGP. So we have a first category, intra-ISP routing. We have some possible representative, OSPF serving as the representative. And we have the routing among ISP, so it's BGP, same. It's a representative of the current category. All right, so in the first discussion, we have a link state. Link state actually, it shows the robustness. However, it should know the entire information. It's not the scalable. However, Distributed one, yes, we have the scalable version, but we have the bad robustness for the distance vector. So later, what to do? And actually, we try to have the scalable one. So making routing scalable. This is the first step. Well, it says our routing study thus far idealized version. All right. We have, for example, for the current link stack, it's the flat one, and we assume all routers behave identically. Therefore, not the routing algorithm for the real situation. So, not true in practice. Therefore, the first issue should be we want to make it scalable. So, scale, we have billions of destinations. It's not the problem for the current, for example, link stack routing algorithm. So, it can store all destinations in routing tables. So that says link stack is not okay at all. But you can have your own scale. If you have the small scale, then it's fine. You still can use it. Well, routing table exchange with swarm links. What that means, swarm links. That says we have a lot of information. Well, later we will check the keyword for you, swarm. And we need to have the consideration of the administrative autonomy. What that means, autonomy? Autonomy says we have some maybe organization, and that organization will have the proper control for some issues. Well, internet, actually we know it's a network of a network. So we have a small network. Small network actually serving as the one of the element of the autonomy. And we have a unified of autonomy, then we have autonomy. Because of the concept of autonomy says, well, each network, each subnetwork try to control its network routing issues. All right, so we already have the two key terms here. All right, this one, swarm and autonomy. All right, and let me stop here and take a rest. Well, so in the first class, actually, I didn't know the second category of the traditional routing algorithm, distance vector. Of course, we didn't have to start to try to have the realistic routing algorithm, and later we will continue. And if no further question, then let us take a rest.